So, good afternoon. My name is Paul de Meulenaren from the University of Antwerp in Belgium. And yeah, the title tells it. I will speak a little bit about software architecture in autonomous systems. It's all about autonomous systems this afternoon. In the meantime, you know what it is, but now software architecture. Software architecture is a concept that can cover many different things. I will only talk about software architecture for deployment. And deployment means getting your software from your computer down to the robot itself, inside the embedded system. And I guess you know what embedded systems are. So you have sensors. The signal comes to the software, the embedded software in the robot, in the car, whatsoever, and then it ends up with the signal going to the actuator such that things are getting to move, for instance. Now, the picture here on the left-hand side, that's something that you have seen before, I think, in the presentation of Peter in the first half of this afternoon. And you have difficult words there, managing system and managed system. So the managed system is just the robot. So don't care about the difficult words. Managed system, that's the robot, that's the mechanical thing that is running about, and that contains a lot of software, mainly control software. And then the thing here on top is the managing system. So it's something smart, like a computer, or so-called smart, trying to manage that robot. And as you have learned today, the management we are talking about today is about adaptivity. So this smart computer, this managing system, is running the so-called Maple K loop that has been mentioned before several times, and that is trying to observe the robot, to think, something is going wrong, I need to adapt myself, and then sending a new plan to that robot. That's in brief the topic of what we are discussing today. But okay, having the software in the managing system, having the software in the managed system, how to control it all and how to get it deployed on the real computers at the end. So that's the question of this lecture, making the self-adaptivity there in the Maple K loop, make it run on real robots. In other words, that's the meaning of the word deployment. And in this project, we do it by the RAP. The abbreviation stands for the RoboSAPIENS Adaptive Platform. That word is not very important here, but that's also mentioned, what we have mentioned before. So I jump to the conclusion, and then I go back to explain what the conclusion is. So the platform, the software architecture that we are proposing here, and I will try to explain a little bit to you, is the drawing here on the right-hand side of this picture. So the left-hand side, you know that. I explained it in the previous slide, and how to orient ourselves in this slide. Well, this managing system, so the computer controlling and governing and changing everything, that's here on the left-hand side. The managed system, the robot, is here on the right-hand side. But of course, you don't recognize the robot. It is a picture of, it's a representation of the software running inside. And here, this is what we call the deployment platform. So I'm quite convinced that you think this is still a silly drawing. I don't understand it. That's very normal. You see lots of colors. That's the only thing you can observe so far that you can conclude. But I will try to explain a little bit why we came up with this silly drawing. So, main question I would like to discuss with you is, why at all would we need software architecture, and more in particular, a software deployment architecture for those embedded systems? Why? So let's start with a simple example with an Arduino. Take an Arduino and start programming this. I have a question to all of you. Who of you know what an Arduino is? I think many of you already played around with it. You can take it as a toy. You can do some more interesting projects as well. So you know what is an Arduino, and that's the main archetype of an embedded system. And here you see some very simple example code that you can run on an Arduino. It's a loop, starting here, line 20 till 26. And then you see here some inputs. It's a sensor value that we read. You might do some calculations, not in this code, but you might do some calculations. And then you have the output, in this case, just a print. That's what we do here as well. In your managed system, in the robot, you have input from a sensor going through some control software, very classic, no adaptation at all so far. And then the result is going to an actuator. Go left, go right, go faster, go slower, that kind of things. That is simple. So far, so good. You can do it with an Arduino. This is a bit more complex. Now we have the Maple K loop included. We have that approach to include self-adaptivity also included here in this simple drawing. It's the green line. Sensors are telling to the software, perhaps inside your Arduino, the sensor values tell you that something is not precedented, not foreseen. It is a bit surprised that some sensor values appear. You start analyzing it. You make plans. You double check the plans, whether they are okay, and then you execute the new plan. So, for instance, you modify the control software. Can this green trajectory also be made in a simple Arduino, just making code like this? The answer is yes. Even very complex software, thousands of lines, you can do it this way. This is deployment without any decent architecture. You don't need an architecture. You just can do it. So, why do we need a deployment architecture? You could do it without, but we have good reasons to still go to an architecture. So, any ideas? Why do we need a deployment architecture? It's told to me that this is a workshop, and I want you to work. Any arguments? I think there are many arguments, and the list I will show here is far from complete, so please speak up. Any ideas? Why? So the alternative is just doing the coding, 5,000 lines of code. It will work, but I say I prefer an architecture. Why would I go to something architecture-like? Yes, please. Yeah, I think you already gave a few very good arguments. At least I recognize two arguments, very good. So you want to reuse things like resource management. It's not something that you invent every time again and again. No, once you solved it, you can reuse it in later projects and later problems. And the second argument I hear is, well, it can be so many things. You need to be organized in some sense. So I think that's basically the main arguments I will bring about in a few minutes. But maybe there are more ideas. Yes? If you do not have an architecture, you might include risks. It might not be safe at the end anymore. That's what you say. Yeah. Yeah. So you have better guarantees on safety. And in the project, we call it trustworthiness. Trustworthiness is a bit broader concept than just safety. So it will indeed augment it. It will help for that. Say, okay, I'm already very satisfied unless someone is eager to bring a new argument. Okay. So that's a bit what we have heard. Many more reasons can be told except these four, but these are the ones I think about. Managing complexity. So embedded systems are sometimes very complex. They have constraints, deterministic real-time behavior, and so on. So it can become complex. So be sure that you, as a software engineer, you master the complexity. Hardware abstraction. So you run it on a microcontroller, on a microprocessor. 1 year later, you want to run the same thing on a different microprocessor. So it's better to reuse your code and not start over from the very beginning. So reusing those things, splitting the hardware from the application can be interesting. That's also something we support from architecture. Modularity, just say software components. Instead of having 5,000 lines of code, split it out in different subparts, call it components, and then you can master it. Then you can overview the complexity. You can reuse those components in other projects later on. It's easier to test. Testability is improved. And you can bring more arguments than just these two. And then something I think I did not yet hear, that is scalability in a team, because you do not work on this project on yourself. You need to collaborate with colleagues. You need to collaborate with other companies. So therefore, you need to make good agreements, not about 5,000 lines of code, but maybe 5 million lines of code. And then you need to distribute the work. You need to have good agreements. And then software architecture is also helping that part. So team scalability, parallel development, and so on. So that's all just a few good arguments. So I will run over some of these arguments and show how we did build up our architecture here. It is not invented by us because there are many other architectures in the world, and we were inspired by different ones. So one of the things we propose here is to have a layered approach. So here at the bottom, you have the computational architecture, let's say the microcontroller or the microprocessor. Up there is the application layer. That's the real software you want to run. That's the algorithm you want to have it executed. So the application layer, the application is, of course, the application-dependent software. New applications require new software, new algorithms. And at the bottom, it's the hardware. The layer here in between, the green one, is the platform layer. That means that the software, while here at the bottom we have the hardware. What's in this software? It's things like drivers. You might know in the hardware you need to play with addresses, go to registers, and having concerns with timings and so on. Well, here we abstract that hardware away such that it is somewhat more human readable, and you can program it through that interface. And the service layer, I will talk about that in a few minutes. So that's separation of concerns. Let's split the application from the hardware. Modularity, that's the components. Because in this application layer, or service layer or platform layer, there can be lots of code. And instead of having a huge spaghetti of code, we want to have more component-like approaches, because then we can master it, we can divide the work, and so on. So, and then this is a drawing I've shown you before. This is the approach we take in the current project. So we indeed have their hardware. We have it twice, because we have here the robot on the right-hand side. We have the server or something in the cloud whatsoever on the left-hand side. We have the platform abstracting these things. We do not do a lot about that in the current project, but here in the services, we do a lot. And I come to that point later. And here in the application, you see that the monitor, analysis, plan, execute, legitimate. So it's the Maple K loop that you heard about. That's part of the application. Of course, the structure is the same, but the content is different, because doing adaptivity on an autonomous ship or doing adaptivity on a warehouse robot, it's the same MAPE-K, but the content is each time different. So that's why it is application specific. That's why we put it here at the top. Okay, so that's the concept we think about. These parts in the service layer I will need to explain. So again, this picture, the service layer, this is meant to be not application dependent. It is meant to be not hardware dependent. It's in the middle there, bringing services such that the application can call for the same service every time and again. Very simple services, not only for this project, but widely used, is send or receive messages. The application wants to send a message to another computer or wants to receive a message from a sensor, for instance. So that is typical services that are being located in the service layer. Maybe a service that you know very well is start a new software task, because that service is also running on your laptop. Because every application you open, every application you start, must be run on the same processor. And then you can have not only one task, you can have 5 tasks, 25 tasks running almost in parallel, but basically it's not in parallel. It is being scheduled by the processor, by the operating system. That's also a service. So that's nothing new. We reuse those things. They already exist for tens of years. And then we have their new services due to that adaptivity, due to the Maple K. And that's what we have elaborated in the last 2 years in this project. So new services for the Maple K. Well, again, you have here the managing system and the managed system. And in the middle there, we have that new layer that we are discussing. That's that RoboSAPIENS adaptive platform. And yeah, Peter already showed this slide before, but now we can look at it from the service point of view, why these things are popping up in our platform. So messages from the robot to that Maple K loop, that's the knowledge gathering, that's a service that we include. Also the other way around. Yeah, after a lot of thinking here in the algorithm, we come to the execute and we send new plans down there. So that's also a service that has been being provided by the service layer. And then this policeman is a trustworthiness checker, checking whether everything that goes up and goes down, it is still good enough. It is compliant to some safety and trustworthiness checks. So that's 3 services at least that we need to include that were not existing before. So, okay, that's again what I've shown. So, and you find them here in the adaptive platform in the service layer here in pink. And here you have that service layer again. And this is just one example of what we can do. I will run over it just to show how it works. Here on the right-hand side, you have the application in the robot, the managed system. Here, left-hand side, Maple Key again. I think you start knowing what this is about. And here, sensor information is being collected in the robot, being transferred through the service layer. We have some software components doing checks and things to the knowledge manager, which will bring it to the knowledge base there, so such that it's compliant to certain formats and agreements that we have made so far. And then this process can start. We can do monitoring, analysis, and so on, based on the trigger that new information is coming in. It is not just running like that. You have some orchestrator. It must be run in a decent way. So also that is connected to a service in our service layer, that the Maple Key is run according to what we wish. And And after execution, we say we need to send a new plan. Sending a new plan, it resides in the knowledge base, and then the trustworthiness manager takes care that, really, if we do modify the robot, if we do modify a car, a ship, whatsoever, that it is still trustworthy, that it's still safe. And after the checks have been done, only then it can be effectuated on the real device. So you see, that is what we do in the service layer, just as an example, perhaps one of the most typical examples. So conclusion, what have we done here? I hope what you have learned. We have proposed a well-known deployment architecture, but we have added components, we have added services. We focused on the separation of concerns, application specific versus the generic part. We hope that we enabled ease of reuse on different hardware platforms, support of legacy applications such that old stuff can be reused. What I did not talk about, but related to this topic, is that you not only need the architecture, you also need tools and workflows to support all this. And something I also did not touch is that you not just have one computer and one robot. It can be distributed over multiple computers with networks in between, distributed platforms. That's also covered here, but I don't have the time to discuss that. That's it from my side. Thank you for your attention.
Thank you, Paul. So the next